Hi, my name is Thomas Pustai. I'm from the Distributed Systems Group at TU Wien in Austria. And me and my colleagues Fabiana Rossi from the University of Rome, Tor Vergata, and Shaham Dusta from TU Wien wrote the paper Pogonip Scheduling Asynchronous Applications on the Edge, which I'm going to present to you today. So our motivation is that schedulers in popular container orchestrators such as Kubernetes work very well in the cloud. But as edge computing is pushing the services to devices at the network edge, we need to consider the heterogeneous resources of these devices and the volatile network links between them, something which is not present in the cloud data center because there all the links have low latency. The devices have many resources. There has been quite a lot of work on edge scheduling for synchronous applications. However, to the best of our knowledge, no one has tried to tackle asynchronous application scheduling. So where the applications communicate through a centralized message queue, which passes the messages from one service to the other in order to decrease coupling between the services. And this is what we're doing with Pogonip. So our contributions are first the formulation of the placement problem as an integer linear programming optimization problem, which places the microservices by considering constraints on the network latency towards the message queue on edge nodes, and if necessary, offloads some services to the cloud. Now, as we all know, the placement problem is NP complete. So we can't just implement the optimization problem and run that on a real-world cluster. We need a heuristic. So for that, we have developed what we call Pogonip heuristic to quickly find an approximate solution. And then the third contribution is a prototype implementation using a Kubernetes scheduler. So for optimization problem, we followed a divide and conquer approach to divide the problem into two subproblems, one for edge placement and one for cloud placement. This, on one hand side, simplifies the placement problem formulation, but also speeds up the resolution phase and allows us to more easily integrate other objective goals. So as I mentioned before, we first try to place on the edge, and only if we don't find enough resources there, we go to the cloud. And the overall goal is to, of course, minimize the total cost, which is the sum of the edge resources cost and the cloud resources cost. And we try to minimize that while ensuring that each application component is either assigned to one edge node or one cloud node. The message queue is placed only on edge node because it needs to be as close as possible to the app's other microservices. Then a component is only placed on a node if it has enough CPU and memory. And a component is only placed on an edge node if its latency to the message queue node is below the app's max latency limit. Now, this does not apply to the cloud nodes, as we will discuss a little bit later. But for the edge nodes, this is a hard constraint. Now, here on the screen, you can see our two heuristic algorithms. On the left-hand side, the one for edge nodes, and on the right-hand side, the one for cloud nodes. So the one for edge nodes gets as input all the applications to deploy. And as output, it delivers a set of microservices which should be forwarded to the cloud and the application placement on the edge cluster. So it iterates through all the applications, and for each application, it first places the queue system because that's the central component of the application. So it filters out all the nodes which don't meet the resource requirements, and then it filters out all nodes whose latency to the control node of the edge cluster, which we assume to be the center, is greater than our max latency requirement. If we don't find any nodes that satisfy all these requirements, then we discard the application. Otherwise, we continue by first computing the number of instances that could be placed on a particular on the current node. So we do that by using the most precious resource on the respective node, so either CPU or memory, depending on which one we have less of. And then once we know how many instances of the message queue we could allocate on that node, we allocate the message queue on the node where this number of instances, this potential number of instances is the greatest, because you want to spread the message queues across multiple nodes so that they don't share the resources on one node. Then we place the microservices of the application on the nodes. So we again filter out nodes that don't meet the resource requirements. Then we filter out nodes that don't meet the latency requirement to the node with the message queue. If we don't find any edge nodes that satisfy our requirements, we add the microservice to the set of microservices to be placed on the cloud. If we find a suitable edge node, then we first compute again the number of instances that we can place on this node. And in this case, we want to allocate the microservice on the node with the minimum value of instances, because we want to maximize the resource utilization on those nodes that we are using and make sure that we can turn off nodes that we don't use. And then in the cloud, it proceeds similarly. So we implemented our heuristic using the Kubernetes scheduling framework. That's the framework that's also used for the main Kubernetes scheduler. So in fact, we build on top of the Kubernetes scheduler. So we reuse most of its original functionality. And the scheduling framework divides the scheduling cycle into a sequence of stages, which you can see here on the lower part of the screen. And for each stage, you can register one or more plugins. Now, there are a lot of default plugins in the Kubernetes scheduler, and here on top you can see the plugins which we added. So first, we want to make sure that we always schedule the message queue first. Then we load the service graph of the application, so that's used to record for us on which nodes, which microservices have been placed, so that we can compute the distances. Then we have 3 plugins, which we will discuss in just a second. And finally, we update the service graph with our final decision. So the latency plugin is very crucial for us, and it has 2 operation modes. So for the message queue pod, it filters out nodes that exceed the maximum latency requirement to the edge cluster's control node. So that's the one here. Now we assume that the control node is the center of the region, and thus proximity to the center should give us good latencies to a large number of other nodes. For microservices, we filter out nodes that exceed the max latency to the app's message queue pod. So if it has been placed on worker 4, we will be calculating the latencies to the worker node 4. And as I mentioned before, that's a hard constraint in the edge cluster. But when moving a microservice to the cloud, it's a soft constraint, because we're following the approach. It's better for the app to run slowly than not to run at all. The NodeCost plugin is quite simple because it just returns a higher score for cheaper nodes. So we assume that edge nodes are the cheapest because we're the ones controlling the edge cluster. And then cloud nodes increase in cost as they gain more resources. The PodsPerNode plugin returns a score based on the number of possible pod replicas that the node could host. And as you saw before in the algorithm, it has two operation modes. So for the message queue pod, having more potential replicas on a node means a higher score. So we favor nodes with low resource utilization to avoid congestion and to be able to spread message queues across multiple nodes. And for other pods, more replicas means a lower score because we want to maximize the resource utilization and power off nodes that we don't use. For evaluation, we used a taxi Internet of Things application, which is based on a demo application from some colleagues of ours. We modified that application to be asynchronous, so we added a RabbitMQ as the message queue system. You can see the requirements here. Then we added so then the application consists of an IoT load generator service and two edge aggregator services, which get the load from the load generator, perform some aggregation, and then forward it to a data storage microservice. So we need to place 4 microservices and, of course, the message queue. So in our first experiment, we want to deploy one instance of this taxi application, and we have this edge-only cluster that you see here on the right. It's based on the specs of the Raspberry Pi 3 Model B Plus and the Raspberry Pi 4 Model B. However, we only simulated all these nodes on one large VM using the kind tool, so Kubernetes in Docker, which is very, very useful. And in our experiment, we had the maximum latency requirement of 50 milliseconds, and we collected the metric, the latency to the message queue. We did 5 runs of each placement strategy, and other than our Pogonip heuristic, we tried the greedy first fit scheduler, then a round robin scheduler, so 2 very classic ones, and then the Kubernetes scheduler, and of course our optimization problem. So on the right hand side here, you can see the results of all 5 runs combined. And as you can see, only Pogonip and opt achieved the max latency requirement, whilst the other schedulers failed. And we're going to take a brief look at how this happened. So the greedy first fit scheduler, of course, always picked the same placement. The message queue ended up in the control node, and then the other nodes, worker 1, 2, and 3 were used. And of course, here the problem is the use of worker 2 because it has this large latency of 80 milliseconds to worker 1. The round robin scheduler performed even worse because, well, in the first iteration, it placed the message queue in the control node, but then at the beginning of the later iterations, so the second and the ones beyond that, the next node pointer was always at worker 4, which was too small to host the message queue. Worker 5 is also too small, so the message queue always ended up in worker node 6, and this, of course, has a very bad latency to the other nodes, and thus we have this bad result here. Kube scheduler did much better, placing message queue in worker 3 and avoiding the control node. Yeah, we can only speculate on why, but probably because it is designated as the Kubernetes master. And yeah, so it actually placed more than half of the nodes on more than half of the pods on nodes with a sufficient latency, but of course then a large number of pods was placed on nodes which did not satisfy our requirement. The Pogonip scheduler, depending on the run, either placed the message queue on the control node or on worker 3, so nodes with very good latency, and it of course avoided worker 2 and worker 6 so as to achieve the latency requirement in all cases. The optimization problem always computed the optimal solution with the lowest average and the lowest median latency. In our second experiment, we then deployed 8 instances of that taxi application. So 1 message queue and 4 microservices times 8. And the message queue must be deployed in the edge cluster. Whereas we also have a cloud now available for the other microservices. The edge cluster consists only of Raspberry Pi 4 Model Bs. And in the cloud, we have 10 small nodes, 10 medium nodes, and 10 large nodes, which is more than enough for our simulation. we have again the max latency of 50 milliseconds, and this time we collect the latency to the message queue, the number of successfully deployed instances, and the number and type of cloud nodes that we use. So here you can see on the left the number of successfully deployed instances. You can see that opt always deployed all 8 instances, and Pogonip deployed either 7 or 6, with the others usually below that. And in terms of latency, none of the schedulers managed to achieve the latency limit for all the instances, but Pogonip and opt at least stayed below that limit for more than half of the instances, or for half of the instances. So what we noticed here is that the optimization problem scheduled more pods in the cloud, so it sacrificed latency for deploying all application instances. Whereas one very interesting thing was that the Kubernetes scheduling framework-based schedulers, which were all the others, they depended on the order that the pods are processed by Kubernetes. So since our message queue was a stateful set and all the microservices were Kubernetes deployments, we noticed actually that some message queue pods were created a while after some of the other microservice pods had already been scheduled. So that's basically a non-deterministic behavior inside of Kubernetes that's due to internal scheduling reasons of these stateful set and deployment controllers. Yeah, opt and Pogonip achieved the lowest possible cloud costs for the pods placed in the cloud. So here we're good as well. The resolution times, so as to justify the use of our heuristics. So you can see for 8 instances, we had these resolution times, whereas we also did some runs with 10 instances, and we had these. And you can see actually that all performed pretty well, but for the optimization problem, you can see actually an increase of 72% of the runtime with just 2 more instances. So this definitely justifies the use of a heuristic. Now, in conclusion, considering edge-specific peculiarities during scheduling definitely yields great benefits. The heuristics achieve good results in a relatively short execution time. And in terms of future work, we want to investigate other performance metrics such as network usage or energy consumption, and also investigate the impact of mobile nodes, such as smart cars. And then, of course, we also would like to investigate service migrations between the nodes, for example, as the smart car moves. With that, I would like to thank you very much for your attention.